Assalamu alaikum dear students, welcome to the 24th lecture of Discrete Structures CSC 102. In the previous lecture we have started Mathematical Induction 1, in which we have studied the basic principle of mathematical induction and methods of proof, and we have proved some properties involving integers. So today we are going to discuss some advanced properties which involve inequalities, a divisibility property and a sequence property with the help of principle of mathematical induction. And at the end of this lecture we shall discuss strong mathematical induction. In the previous lecture we were discussing sum of the geometric series. So this is basically the sum of the geometric series. You have studied it this series in your FSC mathematics first year or second year. This is basically the sum of geometric series, sum from I from 0 to n, r power I is equal to r power n plus 1 minus 1 divided by r minus 1, where r is any real number except 1. If r is 1, then the right hand side is undefined, therefore we restrict here that r is not equal to 1. R could be any other real number, and n is any integer greater than or equal to 0, or you can say n is any non-negative integer. We have to prove that left hand side is equal to right hand side, that is a sum of this geometric series is equal to this. So first we have to prove the basis property of mathematical induction and then the inductive property. As you know, there are two properties or two conditions, statements we have to prove. I have told you in the previous lecture. So first property, the basis property we have to prove is that show that p of 0 is true. We suppose that this whole quantity is p of, you can say, n. So first of all we have to prove it for p of 0, means when n is 0. To establish p of 0, we must show that summation I from 0 to 0 r power I is equal to r power 0 plus 1 minus 1 divided by r minus 1. So we have to show this. So this is obvious. I think you can easily see that r power 0 plus 1 minus 1 over r minus 1, this is basically r minus 1, and this is cancel out is equal to 1. This is right hand side, and the left hand side is basically I from 0 to 0, means there is only one integral value of I, which is 0. The left hand side is here, basically this is r power 0, this is again 1, left hand side is 1, and here we have proved that right hand side is 1, therefore p of 0 is true. Now we have to show that for all integers k greater than or equal to 0, if p of k is true, then p of k plus 1 is also true. So this is basically inductive hypothesis. We have to suppose that this hypothesis is true, and we have to prove that this conclusion p of k plus 1 is true. So we suppose that p of k is true for any particular but arbitrary chosen integer k greater than or equal to 0, that is, let k be any integer with k greater than or equal to 0, and suppose that this p of k is true. This is p of k. Basically we have used k instead of n, so this is true. Now we have to prove that p of k plus 1 is true. That is, we have to prove this expression, means left hand side is equal to right hand side, where we have substituted n is equal to k plus 1, or equivalently we have to prove this. So to prove this is basically an equation. So equation, as usual, we prove equations, we suppose that left hand side, and then after some steps and using some mathematical results and doing some algebra, we try to arrive on the right hand side. So this is basically the method of proving an equation. So we suppose the left hand side from I is equal to 0 to k plus 1 r power I. This can be written as this. You know, we have discussed that sums can be written as in the sequences and summation notations. Here basically this is I from 0 to k plus 1. So the last term we have expanded here, the rest of the k terms are in the summation notation, because this is written as r power 0, r power 1 plus r power 2 plus so on, plus r power k plus r power k plus 1, k plus 1. This is k. So we again summed these terms and the last term is written as it. So now by the inductive supposition, assumption, this quantity is equal to this, as we have supposed that this is equal to this. This is true. So we have written this is equal to this, and now by taking LCM of these two terms, which is r minus 1, we obtain this, and after simplifying by doing some simple algebra and fractions, we arrived at this, which is the right hand side here, which has to be proved. So we have proved by mathematical induction that this sum of the geometric series is equal to this. So we have proved it. Now if you want to use this geometric series to find the sum, if we want to find the sum of this expression 1 plus 3 square, this 1 is basically 3 power 0. 3 power 0 is 1. So 3 power 0 plus 3 power 1 plus 3 power 2 plus so on plus 3 power m minus 2. So this is basically, we have the formula, this must be equal to r power n minus 1 divided by r minus 1, as this is given here, r power n plus 1, sorry. This is r power n plus 1. Now what is r here? R is equal to 3 here, because here we have 3 power 2 and 3 power n minus 2. And what is n? N is basically m minus 2. So we put r is equal to 3 here and n is equal to m minus 2 here. So this is m minus 2 plus 1 minus 1 divided by 3 minus 1, and after simplifying we get this. So the sum of this series or this expression is given by this. Similarly, we can find the sum of this series. As you know, the geometric series this expression basically starts with 1, because here we have I is starting from 0. So this is basically, this expression is 1, r power 0 is 1 plus r power 1 plus r power 2 plus so on plus r power n. So here we have a 1, but in this expression we have 3 power 2, we must have 1 here. So we take common 3 power 2 here, the resulting series is this. Here we have 3 power m. When we take 3 power 2, we get here 3 power m minus 2. So inserting the same sum for this expression we have calculated here, we get this, the sum of the required series. So this is how we can use the geometric series to find the sum of the expressions like this. how we have deduced, how we have derived this series. For example, if we suppose that the left hand side is equal to Sn, how we can deduce that this sum is equal to r power n plus 1 minus 1 divided by r minus 1. Suppose that the left hand side, which is summation I from 0 to n r power I, this is equal to this. We suppose that this sum is equal to Sn. We multiply both sides by r. Here we have r square and rn plus 1. Then we subtracted this from this. We subtracted this, actually this from this. Here on the left hand side we have r into Sn minus Sn, and when we subtract this from this we obtain this. Here r square is cancelled with r square, r is cancelled with r cube is cancelled with r cube, because here we have negative sign. So what is left? Only 1 and rn plus 1 is left. So we get rn plus 1 minus 1. From here we take common Sn, which is r minus 1 into Sn. So now dividing, here we get r minus 1 into Sn. So dividing on both sides by r minus 1, we get rn plus 1 minus 1 divided by r minus 1. So the sum is basically equal to this. This is how we can derive this series. Next is how to prove a divisibility property using the mathematical induction. If we have given an expression, for example like this is divisible by 3, this we have to prove that, this we have to check that whether 2 power 2n minus 1 is divisible by 3 or not. So we can prove such type of properties by using mathematical induction. So this is for all integers n greater than or equal to 0, 2 power 2n minus 1 is divisible by 3. So this is our basically p of n. P of n is 2 power 2n minus 1 is divisible by 3. To prove this property by using mathematical induction, we have to prove the two statements, two conditions of the mathematical induction. The first is show that p of 0 is true when n is equal to 0. When n is 0, we put here 0, n is 0, 2 power 2 into 0, 2 into 0 is 0, so 2 power 0 is basically what, which is 1. 2 power 0 is 1, 1 is cancelled out with 1, we get 0. Now 0 is divisible by 3. It is obvious, we have discussed in the divisibility when we have discussed the quotient remainder theorem and the divisibility property of the integers. Now we have to prove that if for all integers k greater than or equal to 0, if p of k is true, then p of k plus 1 is true. So this is basically inductive supposition and this is conclusion. We suppose that this is true and we shall prove that this is also true. So we suppose that 2 power k minus 1 is divisible by 3, means p of k is true. Inductive hypothesis means this is true for all k greater than or equal to 0. This is true. Now we have to prove that p of k plus 1 is true, means 2 power 2 into k plus 1 minus 1 is true. To prove this, we consider this 2 power 2k plus 1, we multiply 2 inside, we get 2k plus 2 minus 1. We can write it as 2k into 2k. We have used a power n into a power m is equal to a power n plus m. We have used this property here in this expression Now this can be written as 2 power 2k into 2 square. 2 square is 4, and 4 can be written as 3 plus 1. Now we have multiplied this term with 3 and with 1. So this is basically written as 3 into 2 power 2k plus 2 power 2k minus 1. So this can be written as this. Now 2 power 2k minus 1 is basically divisible by 3 by the inductive hypothesis, as we have supposed that this 2 power 2k minus 1 is divisible by 3. So this expression is divisible by 3, and this expression is basically multiple of 3. If it is multiple of 3, then obviously it is divisible by 3. So therefore this expression is also divisible by 3. This expression is also divisible by 3. Therefore if we have two expressions divisible by 3, then their sum is also divisible by 3. Or we can proceed further. We can write it as 3 into some integer r, and by taking 3 common from these two terms, we can conclude that this expression is a multiple of 3. If this expression is a multiple of 3, then it is divisible by 3. So p of k plus 1 is also true, because this expression is divisible by 3. So by the principle of mathematical induction, we can say that, so by the principle of mathematical induction, p of n is true for all n greater than or equal to 0. We can say that. So we can prove a divisibility property or an expression like this by using the principle of mathematical induction. Next is proving an inequality. This is also important to discuss here, how to prove an equality which involves integers. So here we have to prove that for all integers n greater than or equal to 3, 2n plus 1 is less than 2 power n. For that again, but to prove it, this is p of n, basically this is p of n here. So to prove this inequality by using principle of mathematical induction, we shall prove it that this is true for p of 3, because n is starting by 3, because a is 3 here. So first we shall prove that p of 3 is true. So by inserting 3 here, 3, n is equal to 3 here and n is equal to 3 here, we shall check whether the inequality is true or not. So if we put n is equal to 3 here, 2 3s are 6 plus 1 is 7, and 2 power 3 is 8. So 7 is less than 8, so this is true. This inequality is true because 7 is less than 8. So we can say that p of 3 is true. Next, the same step, we show that for all integers k greater than or equal to 3, if p of k is true, then p of k plus 1 is also true. We suppose that the hypothesis is true, inductive hypothesis is true, and we shall prove that the conclusion p of k plus 1 is true. So we suppose that k is any integer such that k is greater than or equal to 3, and this is true. This is basically p of k, and we must show that p of k plus 1 is true. Means we replace k by k plus 1 in the given expression, and we shall prove that this or this is true. This is basically p of k plus 1. So to prove this, we consider the left hand side. 2k plus 3 is equal to, can be written as 2k plus 1 plus 2, because here we have 2k plus 1, therefore we split this 2k plus 3 into 2k plus 1 plus 2, so that we can use this inductive hypothesis. We do usually the same step. The idea of proving pk plus 1 is basically always this: we use the hypothesis p of k in proving k plus 1. Otherwise it will be very difficult to prove this is less than this. If we use the inductive hypothesis, it will become you can say simple and easy. So we write it as 2k plus 1 plus 2. So now 2k plus 1 is less than 2k by using inductive hypothesis. This we can say that 2k plus 1 plus 2 is less than 2k plus 2, as this is less than this, therefore this is same as 2. Now 2 is basically less than 2 power k, because k is greater than or equal to 3. Yes. Now we can write, instead of this, we can write this is further less than 2k plus 2k, which is 2 power, or this is equal to 2 into 2 power k, because it comes 2 times, 1 into 1. So this is 2 power 2k. This can be written as 2k plus 1, because here we have 1. So 2 power k into 2 power 1. We, by using this property, a power n plus into a power m, this is a power n plus m. So this becomes less than this, and we have proved that p of k plus 1 is true. So by mathematical induction we can say that this property is true, that is, for all integers n greater than or equal to 3, 2n plus 1 is always less than 2 power n. Now another situation where we can use mathematical induction and principle of mathematical induction. If we are given a sequence like this, ak, a recursive sequence in which define a sequence a1, a2, a3 and so on, in which the first term is like this, first term a1 is 2, and the next term is, each next term is a multiple of 5 into the previous term. This is such type of sequence is basically a recursive sequence, and we have discussed such type of sequences in the sequences section. Write the first 4 term of the sequence, the first part of this question. The second part is, it is claimed that for each integer n greater than or equal to 0, the nth term of the sequence has the same value that given by the formula 2 into 5 power n minus 1. In other words, the claim is that the terms of the sequence satisfy this equation. That is, we can write this sequence like this. So prove that this is true. We have to prove that this is true. First we shall solve the first part, a part. The first 4 terms of the sequence are a1 is 2, this is given, a2 is 5 into a2 minus 1, because here we have ak is equal to 5 into ak minus 1. If we put k is equal to 2 here, we get 5 into 2 minus 1, which is 5 into a1, and a1 is given here 2. 5 into 2, 10. This can be written as further 2 into 5 power you can say 2 minus 1. We can write 10 as, because 5 power 2 minus 1 is 1, 5 power 1 is 1, 5 power 1 is 5, and 5 into 2 is 10. Now a3 is 5 into a3 minus 1, which is 5a2. Now a2 is 10. We can write here a2 is equal to 10. 5 into 10 is 50. Now this can be written as 2 into 5, 3 minus 1. because 3 minus 1 is 2 and 5 power 2 is 25 and 25 into 2 is 50. Similarly, A4, this is basically the subscript A4 here. This is equal to 5 into A4 minus 1. This is A3, and A3 is given by 50. So if we replace A3 by 50 here, we get 250, which can be written as 2 into 5 power 4 minus 1. 5 power 4 minus 1 is 3. 5 power 3 is 125, and 125 into 2 is 250. So by generalizing like this, by doing the same exercise, we can arrive at that an can be written as 2 into 5 power n minus 1. So you can proceed like this, and you can arrive at the conclusion that an is equal to 2 into 5 power n minus 1 for all n greater than or equal to, you can say, 1, because if we put 1 we get a1, and here 2 into 5 power 1 minus 1 0, 5 power 0 is 1, and we get a1 is equal to 2, which is the first term. Similarly, we can obtain the second, third, fourth, and so on, all the terms of the sequence. Here p of n is an is equal to 2 into 5 power n minus 1. First we shall prove that p of 1 is true, that is when n is 1, 5 power 1 minus 1 is basically 0, and we get 2. Then we suppose that p of k is true, that is we shall suppose that ak is equal to 2 into 5 power k minus 1 for all k greater than or equal to 1, and then we prove p of k plus 1, which is ak plus 1 is equal to 2 into 5 power k plus 1 minus 1. So first we have shown that p of 1 is true, means we put n is equal to 1, n is equal to 1 here. So this is what? This is 2 into 5 power 0, which is 2. So we get 2, and we are given that a1 is true, so therefore p of 1 is true. Then we suppose that p of k is true, the inductive hypothesis, and we have to prove, we have supposed it here, ak is equal to 2 into 5 power k minus 1, and we have to show that ak plus 1 is equal to 2 into 5 power k plus 1 minus 1, or this can be written as, because 1 is cancelled out with 1. So to prove it, we suppose the left hand side ak plus 1. So by definition of this sequence given at the start, ak is basically equal to 5 into ak minus 1. So we can write ak plus 1 is equal to 5 into a sub k plus 1 minus 1. Here 1 is cancelled with 1, we have 5 into ak. Now ak can be written as, by using this, ak is basically 2 into 5 power k minus 1. So here we can write, instead of ak, 2 into 5 power k minus 1. So we write 2 here and 5 here. We write 5 here and 2 here, we can interchange. So this basically 5 power 1 we have here, and here we have 5 power k minus 1, and using that property which I have written here in earlier slides, this property we can write here 5 power 1 plus k minus 1. 1 is cancelled out with 1. We get 2 into 5 power k, which was required. We had to prove this. So by principle of mathematical induction, we have concluded that we can write this sequence like this, or this is true for all integers n greater than or equal to 1. Next is another example. We have to prove this property by using principle of mathematical induction, where this is basically p of n. Now to prove this property, we follow the same procedure, and we have to prove that this property is greater than, say this is true for all n greater than or equal to 1. So we shall prove first that p of 1 is true when n is 1. We can easily see that when n is 1, we on the left hand side we get only the first term here when n is 1. So this is, we obtain this 1 plus 1 over 1 is basically 2, and if we put on the right hand side n is equal to 1, we get 1 plus 1 is equal to 2. So 2 is equal to 2 here. So therefore left hand side is equal to right hand side, and we can say that p of 1 is true for Pn is equal to 1. Now we have to show that for k greater than or equal to 1, if the property is true for n is equal to k, then it is true for n is equal to k plus 1. That is, we have to prove, we shall suppose that p of k is true, and we shall prove that p of k plus 1 p of k plus 1 is true. So we supposed here that this is true for k, and we must show that this is true for k plus 1. So we shall suppose the left hand side, and then we shall prove the right hand side. We suppose the left hand side, and this is equal to this, and until here we can use the hypothesis, as I have told you, that we use p of k in proving p of k plus 1, otherwise it will be impossible to prove it. So this is equal to k plus 1, and by taking LCM and by doing some simple algebra, we can prove that this is equal to this, which was required here. So by principle of mathematical induction, this property p of n, which is equal to this, is true for all n greater than or equal to 1. Next is another problem. I left it, I want to leave it for you as an exercise. You try it to prove by using the principle of mathematical induction. So for each positive integer n, let p of n be the property. This is basically an inequality. 2 power n less than n plus 1 factorial. So first of all, for each positive integer n, so for each positive integer it comes for n greater than, basically if we write 1 here, n is equal to 1. For each positive integer n, this n must be greater than or equal to 2. There must be this property. If not, if we choose n is equal to 1, then this property, this inequality is not true, because we get 2 power 1 is less than 2 factorial. 2 factorial is 2. So there must be this condition, n is greater than or equal to 2. So if n is greater than or equal to 2, then for the first value of n, that is true, we have to check p of 2 is true. Then we suppose that p of k is true, and then we have to prove p of k plus 1 is true. So you will follow these 3 steps, these two 3 steps which we usually do in the principle of mathematical induction in proving some inequality, and I hope you will be succeeded to prove in proving this inequality. The next is another example of the divisibility property, which is basically 7 power n minus 1 is divisible by 6 for each integer n greater than or equal to 0. This we have to prove. We shall follow the same procedure as we do in the principle of mathematical induction. First we shall prove it for n is equal to 0, and because 7 power 0 is 1 and 1 minus 1 is 0, and 0 is divisible by 6, this property is true for p of 0, means for n is equal to 0. And then we suppose that this property is true for n is equal to k, and we shall prove that this property is true for n is equal to k plus 1. Here we have supposed that this property is true for n is equal to k, that is 7 power k is minus 1 is divisible by 6. This is true for all k greater than or equal to 0. And then we must show that 7 power k plus 1 minus 1 is divisible by 6. So we suppose this 7 power k plus 1 minus 1, and this can be written as 7 into 7 power k minus 1. This 7 can be written as 6 plus 1, because we have to use this property. So we write it like this, 7 plus 1, so that we can separate 7 power k. So this if we multiply 7 power k into this parenthesis, we get 6 into 7 power k plus 7k, and 7k minus 1 we can combine. Now by using p of k, that is this supposition, 7 power k is divisible by 6. Now this is the multiple of 6, this term. Now we have two terms which are divisible by 6, then obviously their sum is also divisible by 6. So we can say that p of k plus 1 is true, and by the principle of mathematical induction, the given property, that is 7 power minus 1 is divisible by 6 for all n greater than or equal to 0, for all integer n greater than or equal to 0 is true. Now we move to strong mathematical induction. So what is the definition of this strong mathematical induction? Let p of n be a property that is defined for integers. P of n, basically this property is same, but the method is a little bit different, but overall you can say this is the same method. The only difference that is in the strong mathematical induction is given in the first statement. We'll see it now. P of n be a property that is defined for integers. It could be divisible property, it could be inequality, it could be property of sequences, as we have discussed in previous slides. And let a and b be fixed integers such that a is less than or equal to b. Here we have two integers, two additional integers a and b, such that a is less than or equal to b. Suppose the following two statements are true. P of a, again a is basically the initial step in the principle of mathematical induction, which was the basic step for n is greater than or equal to a. Now a is less than or equal to b. The first property is that p of a is true, p of a plus 1 is true, p of a plus 2 is true, and so on until p of b is true. That is, all these expressions for the given property, or for the given property is true for all the integers from the starting a until the integer b. All these for all these integers the given property is true. The first basis step is this, which is basically a rather more strong property, basis step. The second step in the strong mathematical induction is that for any integer k greater than or equal to b. Now we are saying that we have already proved in the basis step that the given property is true for a until b. Now the second step starts with the b. We say that for any integer k greater than or equal to b, if p of I is true for all integers from I from a through k, means if the given property is true from a through k, now k is greater than b, then p of k is true. So this is basically inductive step. So both of these properties are a little bit strong or stronger than the two properties or two steps involved in the mathematical induction. Then we say in general that the statement for all integers n greater than or equal to a, p of n is true. By saying that by the strong mathematical induction, we can say that for all integers n greater than or equal to a, p of n is true. Here the supposition that p of I is true for all integers from integers I from a through k is called the inductive hypothesis. Another way to state the inductive hypothesis is to say that p of a plus 1 until p of k are all true. We suppose it, and then we prove that p of k plus 1 is true. An example of this, we have to prove that any integer greater than 1 is divisible by a prime number. So we have to prove it by using strong mathematical induction. So let the property Pn be the sentence n is divisible by a prime number for all n greater than 1. So we have to prove that p of 2 is true, p of 3 is true, and so on. Show that p of 2 is true. To establish p of 2 is true, we must show that 2 is divisible by a prime number. As 2 is a prime number, so 2 is divisible by a prime number, 2 is divisible by 2. So we can say that p of 2 is true. Now we have to show that for all integers k greater than or equal to 2, if pi is true for all integers I from 2 through k, means now we are supposing that this property is true from 2 through k, means for k is equal to 2, for k is equal to 3, for k is equal to 4, 5, and so on until k. This property is true for all these integers, and then we have to prove that p of k plus 1 is true. So let k be any integer with k greater than or equal to 2, and suppose that I is divisible by a prime number for all integers I from 2 through k. We have supposed that this is true, and this is our inductive hypothesis. We must show that k plus 1 is divisible by a prime number. So we have two cases here again. If k plus 1 is prime, then k plus 1 divides k plus 1, and we are done, because k plus 1 is divisible by some prime number. If k plus 1 is not prime, then what happens? Then k plus 1 can be written as a product of two numbers a, b, where a and b both must be greater than 1 and less than k plus 1. By using the quotient remainder theorem or divisibility properties, as you can see here that 1 a must be greater than 1 and less than k plus 1. Similarly, b must be greater than 1 less than k plus 1. It means a must be greater than or equal to 2, less than or equal to k. We need only a. We can say that b can only this satisfy can b only also satisfy this property, but we don't need it. It's enough that a is greater than or equal to 2 and less than or equal to k. Similarly, we can say b is greater than or equal to 2, less than or equal to k. So by inductive hypothesis, a is divisible by a prime number p. Why? Because here we have supposed that I is divisible by a prime number for all integers I from 2 through k. Means here a is from 2 to k. It could be any number. Thus a is any number from 2 to k, and we have supposed that I is any number from 2 to k and it is divisible by a prime number. So we can say that by using inductive hypothesis, a is divisible by a prime number p. P is any prime number. In addition, because k plus 1 is equal to a into b and a is divisible by a prime number, then by transitive property we can say that k plus 1 is divisible by a prime number. So regardless of the case that k plus 1 is prime or not, it is divisible by some prime number. So we can say that p of k plus 1 is true, and we are done. We have proved that by the strong mathematical induction that any integer greater than 1 is divisible by a prime number. So this is basically almost same procedure, but the technique of proving the statement is little bit different, and this that's why it's called strong mathematical induction. So in today's lecture we have studied some of the geometric series, and we have studied also, we have proved that the sum of the geometric series by using the principle of mathematical induction. We have proved an example of the divisibility property by using mathematical induction. We have proved one of the inequalities again by principle of mathematical induction, and a sequence property, a sequence. And at the end we have discussed strong mathematical induction, and I have given you one example of the property in which we have proved by using strong mathematical induction. So for today it's enough, and in the next lecture we shall start a new topic, which is counting and probability. Until the next lecture, Allah Hafiz.